My name is Rishabh and I am from CSE AML branch of second semester. Today in this PPT, I am going to talk about the 10 optimization on linear search. Introduction to searching. Searching is the process of locating a specific element inside a data structure such as an array or a list. It is one of the most common and important operations in computer science. There are different searching techniques like linear search, binary search, and hashing based search. In this presentation, we focus on improving linear search. What is linear search? Linear search is the simplest searching algorithm. It checks each element one by one, starting from the first position. The search continues until the element is found or the entire list has been checked. Time complexity. The best case is big notation of 1, the worst case is big notation of n, and the average case is big notation of n. Basic working of linear search. Algorithm steps. So there are 4 steps we include in this algorithm. We have to start from the index 0. Compare each element with the target. If the match element is found in the list or array, we have to return that index. If the array has ended without searching or without returning any of the index, we have to return -1. Linear search does not require sorted data, which makes it flexible but sometimes inefficient. Important characteristics: works on both sorted and unsorted arrays, does not require any pre-processing, performs sequential comparison, suitable for small data sets array. Key observation: in worst case, it may compare every element in the array. Limitation of linear search. Although simple linear search has drawbacks, takes longer time for large data sets. Worst case requires checking all the elements, not efficient when frequent searches are required. Performance does not improve automatically with data size. Main issue: linear search follows a fixed sequential approach and does not adapt based on previous searches. It treats every search independently even if the same treatment is searched multiple times. Because of this non-adaptive nature, its efficiency does not improve automatically with usage. Why do we need optimization in linear search? After understanding the limitation of linear search, it becomes clear that improvements are necessary, especially when dealing with large data sets or repeated searches. Although the worst case line complexity remains O of n, we can still reduce unnecessary comparison and improve practical performance by modifying how the search is performed. Optimization focus on reducing extra checks inside the loop, improving average case performance, making repeated search faster, utilizing data properties like sorting. Even small improvements in the comparison operation can significantly improve the performance when the database size becomes large. This is why different optimization techniques are applied to linear search. Optimization in linear search. Linear search is a simple but it has performance limitation. Instead of replacing it completely, we can improve it by modifying its working strategy. These improvements are called optimization. Optimization does not change the overall time complexity O of n, but it reduces unnecessary comparison and improves practical efficiency. In this section, we will study 10 important optimization techniques used to enhance linear search. Sentinel linear search. Sentinel linear search is an optimized variation of basic linear search algorithm. It is designed to reduce the number of conditional checks performed during each iteration of the loop. In a normal linear search, every iteration performs two checks: whether the index is within the array boundary, whether the current element matches the target value. This repeated boundary checking increases the total number of comparisons, especially for large arrays. Move to front method. The move to front method is based on idea that frequently searched elements are likely to be searched again. When an element is found during linear search, it is moved to the first position of the array and the remaining elements shift one position to the right. For example, if the array is 10, 25, 30, 40, 50 and we search for 40, the updated array becomes 40, 10, 25, 30, 50. This makes future searches for 40 faster. Although the worst case time complexity remains O of n, the average search time improves significantly when repeated searches occurs. Transposition method. The transposition method is a self-organized optimization used in linear search. Instead of moving a found element directly to the front, it swaps the element with the one just before it. This gradually moves frequently searched element towards the beginning over multiple searches without making a large change to the array. For example, if we take an array of 10, 25, 30, 40 and 50 and we search for 40, the updated array becomes 10, 25, 40, 30, 50. In this case, we have just swapped the elements 30 and 40. If 40 is searched again, it will move further forward. All through the worst case time complexity remains O of n. This method improves average performance in repeated search situations. Early termination for sorted array. Early termination is used when an array is sorted in ascending order. In normal linear search, every element is checked even if a further element cannot match the target. In this method, the search stops as soon as the current elements becomes greater than the target value, since all the following elements will also be greater. For example, if we take an array of 5, 10, 15, 20, 25 and we search for 12, the search stops at 15 because 15 is greater than 12. All through the worst case time complexity remains O of n. This approach reduces unnecessary comparison in sorted array. Two-way linear search. Two-way linear search improves the basic approach by checking elements from both the beginning and the end of the array at the same time. Instead of moving in one direction, two pointers are used, one starting from the left and one from the right, and both move towards the center until the elements is found. For example, if the array is 4, 8, 12, 16, 20, 24 and we search for 20, we compare 4 and 24 first, then 8 and 20 where the element is found. All through the worst case time complexity remains O of n. This method can reduce the number of iterations in practice. Loop unrolling. Loop unrolling is an optimization technique where multiple elements are checked in a single loop iteration instead of checking one element at a time. In normal linear search, the loop compares one element per iteration. In loop unrolling, the algorithm may compare two or four elements in one iteration, reducing loop control overhead. For example, instead of checking only an array of I, we checked array of I plus 1 and array of I plus 2 together in one step. All through the overall time complexity remains big notation of On. This technique improves practical performance by reducing the number of loops execution. Immediate break technique. The immediate break technique ensures that search stops as soon as the target element is found. Instead of counting the loop unnecessarily, the algorithm exits immediately using a break statement. In some implementation, programmers use extra flag or allow the loop to continue even after finding the element. This causes unnecessary comparison. For example, once the target is matched at a certain index, the loop terminates instantly without checking the remaining element. Although this does not change the time complexity of O of n, it avoids extra operation and makes the code cleaner and slightly more efficient. Cache-friendly access. Cache-friendly access takes advantage of how modern computers use CPU. Cache memory. When elements are stored and accessed sequentially, the processor can load nearby elements into cache, making access faster. Linear search naturally follows sequential memory access, which improves spatial locality and reduces memory access time. For example, when searching through a large array sorted in cognitive memory, accessing elements one after the other allows the CPU to fetch them efficiently. All through the time complexity remains O of n, cache-friendly access improves real-world performances, especially for large datasets. Index memory technique. The index memory technique improves performance by remembering the position of recently found element. Instead of always starting the search from the beginning, the algorithm can begin near the last known position. This is useful in the case where the same element are searched repeatedly or when the data access patterns are predictable. For example, if an element was previously found at index 6, the next search for the same element can start near at the index instead of 0. All through the worst case time complexity remains O of n, this approach improves average performance in repeated and localized search scenarios. Hybrid approach. The hybrid approach combines the linear search with other searching techniques to improve overall efficiency. Instead of depending only on the basic linear search, it adapts based on the nature and the structure of data. This makes the searching process more flexible, suitable for different real-world situations. For example, if the data becomes partially sorted, linear search can be combined with binary search. In case of frequent lookups, hashing techniques can be used alongside linear search. This flexible approach allows the algorithm to adapt depending on the data size and structure. Although the worst case time complexity of linear search remains O of n, hybrid strategies significantly improve practical performance in real world applications. Conclusion: linear search is a simple and easy to implement searching algorithm that works well for small or unsorted datasets. However, its main limitation is the O of n time complexity due to sequential comparison. The optimization technique discussed, such as Sentinel, move to front, transposition, two-way search, and hybrid approach, help reduce the unnecessary comparison and improve practical performance. Although the worst case complexity remains O of n, these methods significantly improve average case efficiency in real-world application. Thank you.